Alright, welcome back. So let's talk about program memory. And this is a totally separate memory from where the file registers are stored, the general data that we use to store, counters and flags and things like that. This is a completely separate physical memory. This is characteristic of RISC machines, by the way. The old CISC machines, Intel processors, and so on, single memory, okay, that contains both code and data. It gets split internally, but architecturally single memory. RISC machines typically two memories, one for data, another for code. So the code or program memory looks like this. And we think of it as being 16 bits. It's really 8 bits wide, but our instructions are all 16 bits, right? Or, in a few cases, like the MOVEFF instruction, 32 bits, because there's a 16-bit piece and another 16-bit piece. So we think of the memory as 16 bits wide, and there's addresses, and if we're thinking of it as 16 bits, the addresses go up by 2s. And what's the biggest address? Well, it's some huge number. Okay, this whole memory is, approximately 1 million instructions. Well, we don't get 1 million instructions on our processor. We have 1,000 instructions available. So this will go up to 1023. That's the memory that's available on the PIC processor. And all the rest of this is unavailable. But again, different processors, different memory configurations. Some have 2048 instructions. In fact, the PIC 18F1230 is almost exactly like the 1220, except it has twice as much instruction memory. So your instructions go up to 2047. Other processors have more memory available. I don't know which ones have the full million available. So the address is actually 21 bits. Now, 8-bit processor, everything's thought of as being in 8-bit chunks. So on our processor, the address of an instruction, 8 bits, and then a few extra bits in this next 8-bit chunk. And this upper 8-bit chunk doesn't get used by us. It's always 0. Okay, so when the processor is running, it needs to pull an instruction out of memory, right? Fetch, decode it to figure out what to do, and then do. So fetch, decode, execute. That fetch means, go into the program memory, pull out the next instruction, the next pattern of 1s and 0s that corresponds to the instruction we should execute next. And that's done using something called a program counter, or a PC. So the PC accesses the program memory and an instruction is pulled out. And if you look at this simplified picture of the PIC processor, right? Here's the program counter that gets sent over to the address of the program memory, right? And then the program memory, the contents of that comes out and gets saved, and that gets processed by the system. And I misspoke, it's not 1024 instructions, it's actually 2048 instructions. 4 kilobytes, so 2,000 instructions for our PIC processor. Alright, and this program counter is incremented by 2 after each instruction. Why? Because the first instruction when we power on is instruction 0. So PC is initialized to 0. the processor pulls that 16-bit pattern out of memory, starts to decode it and execute it, and when it's done, PC should get changed to 2, because that's the address of the second instruction. So a 2 is sent to memory, that instruction is pulled out, it's decoded, it's executed, and now the PC is changed to a 4, that's the address of the third instruction. That's fetched, decoded, executed, PC is changed to 6, and so on. So after each instruction, your program counter goes up by 2. Alright, so let's MPLAB this. Alright, so I'm writing some random code here. NOP is no operation. So this instruction right here doesn't do anything. It's just a way to sort of waste a clock cycle. Most machines have no ops available. And the clock ticks, but nothing happens. So for...
So there's technically no...
Say again?
So technically, NOP, there's no reason for it besides leaving a space.
Pretty much, yep.
I guess.
Yeah, it literally does nothing except waste a clock cycle. So let's look at the details of it. Nope, no operation. Doesn't take any operands. What's the operation? There is no operation. It doesn't affect any status. Description, no operation. But it takes one word of memory, that's 2 bytes, and it takes 1 clock cycle. There's a decode. There's no fetching. There's no executing going on. And there's no example of what this does. Right? It's at first glance a useless instruction. But it's actually useful if you want to spend some time. For example, if you wanted to write something that took a millisecond, right? Something that would sleep for a millisecond and then add 1 to a counter and display that on an output. So you're making a clock, for example. You could execute a bunch of no-ops, right? And take however much time you want by repeatedly executing these instructions that do nothing. So that's one use for them. The bigger use for them originally was that we didn't have assemblers. We had to write this code as 1s and 0s by hand, and if you needed to insert an instruction somewhere, it would change a bunch of your code because things got moved around. So you'd leave no ops in place so that if you found you had to go back and add an instruction, you'd replace the no op with the instruction you wanted, and things wouldn't end up moving as a result. So I'm just using some no ops in here just as placeholders for no particular reason. And let's run this code. Let's write this code correctly, and then let's run this code. And there's a field up here on the top which says PC:0x0. That's constantly showing me what the program counter is equal to. But I can also I can also look at it as a special function register called PCL. Alright, so when you start, your program counter is initialized to 0, and at location 0, what do we find? So this is the assembled version of our code. This is the stuff we wrote over here on the right. This is how it translated it into its own version of assembly language. This is the ones and zeros for the machine code. And these are the locations in program memory here on the left. 0, 2, 4, 6, 8, 10, 12, and so on. So at location 0, we have 2B80 stored. That's the instruction corresponding to increment file register 80. And after this instruction executes, file register 80 should be incremented. And after it executes, the program counter is going to get incremented to a 2. It's currently 0, it always gets bumped up by 2, and when it increments to 2, it's going to be pointing to this next instruction. So if I go back here and I just say step 1 instruction, program counter is 2 up here, program counter low byte is 2 down here, and file register 80 got incremented because I did that for something to do. Since the program counter is 2, what's about to get executed is the instruction stored at location 2, which is this move LW 7F. And the debugger is letting you know that by highlighting this line of code. I think I stopped my... It's highlighting this line of code in green, right, to say this is the instruction about to be executed. PC is 2. If I say go ahead and execute that, it moves 7F into the W register. The PC is now equal to 4. You can see PC is 4 up here now, and it's about to execute the instruction at location 4, which is this instruction, the move WF addcon 1, which is what the debugger is highlighting. And each of these instructions takes 2 bytes, right? They're 16 bits. So where this instruction was stored at location 0, this was at 2, this was at 4, this was at 6, and so on. Alright, so I'm about to execute the no-op. That's at location 6. We execute that. I hit the wrong button. Alright, we're about to execute the no-op. Our program counter is now 8. And we're about to execute move FF. Okay, move FF is one of these special instructions. It takes 32 bits to code. Move FF is actually coded as this 8-bit pattern followed by this 8-bit pattern. So the move FF is at location 8. The following instruction is actually at location 12, C in hex. So if I look back here, my program counter is 8. That's the address of this. After this gets executed, the program counter will not be 10, but it'll be 12. So let's execute the move FF, and you can see program counter jump to 12. So there's 2 things going on here that you're going to need to work with in coming assignments. One thing is understanding where these instructions are stored in memory. And when you write assembly language code, the instructions are stored one after another, which means usually the address of the next instruction is your current instruction's address plus 2. But in a few cases, like move FF, the following instruction will be your current instruction's address plus 4. And how do you know the difference? It's in your data sheet. So all of these instructions are 2 bytes, 2 bytes. Move FF is 4 bytes. And you can tell that because there's 16 bits followed by another 16 bits. Okay, call is another 2-word instruction, so 16 bits, 16 bits. So a call, the address of the next instruction will be the current instruction's address plus 4. And go to is the same way. That goes up by 4 instead of 2. And LFSR, which we'll talk about later on, is another 2-word instruction. And I think that's it. Everything else is a single word. So let me make all of these the same. Alright, so I've got some more code in here. Let's just compile this and take a look at the assembly language listing. So my first instruction, increment F, that's at location 0, move LW, move F, increment F. Those go up by 2, so 0, 2, 4, 6. Our move FF is at location 8. Now we already worked through that one and saw that the next instruction will not be at location 10, but it will be down at location 12. That's the increment. Why? Because move FF takes 2 instruction words, 4 bytes. Okay, the increment takes 2 bytes. That's currently at location 12, so the next instruction will be at location 14. That's the go-to statement. Go-to also takes 4 bytes. So this is at location 14. The next instruction will be at location 18. That's the increment. Increment takes 2 bytes, so the next instruction will be at location 20 or 14 hex. That's the branch. Branch only takes 2 bytes. Go-to takes 4, branch takes 2. So if branch is at location 14 hex, the next instruction will be 2 bytes later at 16 hex. So you want to understand where these addresses come from based on what the instructions are. Okay, and the first way to know the address of an instruction is take the previous instruction, and generally you add 2, but if it's a special instruction, add 4. Okay, which ones are special? Call, go to, move FF, load file, select register. I think those are the only 4. But look in the data sheet. And remember, when we're writing assembly language code, what we're doing is we're defining a bunch of 1s and 0s that are going to get loaded into the program memory of the processor. So we know that the instructions and the operands and the comma 0 and all of that will go into forming this pattern of 1s and 0s, right? Which tells us what the contents of memory is going to be for each instruction. But we also need to understand where that contents is stored. Okay, starts at 0, goes up at 2, 4, 6, and so on, but for some of these you jump up by 2. Okay, so this brings us to this origin statement. In the beginning of my code I said origin 0x00. Suppose I had said origin 0x12, and I reassemble. Well, guess what? My first instruction is not stored at location 0. Where is it stored? Location 12. Why 12? Because I said that's what the origin is. So origin says where should the next instruction be stored. Since I said origin 12, the increment got stored at 12, the move at 14, the move WF at 16, and so on. What if I had said origin 11? I got a problem. And the problem is absolute code section origin 0 must start at a word aligned address. That's a fancy way of saying your origin has to be even. Right? Why? Because we've said in our memory map here that these things are always indexed by even numbers. So trying to say start at location 11, it's like, no, I'm not going to do that. But if it's an even number, that'll work fine. Okay, so trick questions. Where is this increment going to get stored?
Zero?
Going to get stored at 0. If I had had an instruction after this statement, it would have gotten stored at location 12. But this is a comment. This doesn't get assembled. And this doesn't get assembled. So if I build this, my code just starts at location 0. This is a little strange looking, but perfectly legal. So I have an origin 12 statement up here. I have some code. I have an origin 40, more code, and an origin 0. Well, it does exactly what you kind of think. It starts writing this code at location 12. There's the increment, the move LW, the move WF. And now I say origin 40, so the next statement, this increment F, gets stored at location 40. And those instructions all get stored sequentially, skipping by either 2 or 4, until I come down here, this branch top where I said origin 0, so that branch got stored at location 0. So you have absolute control over how the program memory ends up on this processor. And for first order work, you know, we just want to start at 0 and go sequentially, but as we move into dealing with more hardware, we're going to start wanting to control where our instructions are placed in memory. We're going to want some things to be at very specific locations, and so we're going to start using this origin statement a lot. The other thing I want you to notice is that, let me add some other things in here. So I've written some other statements in here. I've got an include statement, an origin, an equals, a define, another equals. There's no assembly language code. There's no machine language code being generated from those instructions. There's no binary pattern corresponding to z equals 81, define y 12, origin 12. These are called directives, okay, or assembler directives. They're things that tell the assembler, that tell MPLAB what to do, but they don't actually generate code. No code, no code, no code, no code. Top is a label. It says when I say branch to top, this is where I want to go, but that doesn't actually generate any code. The first thing of all of this that actually generates any machine code is this increment file register. And it generates a 2B80, and so that gets stored at location 12. This origin statement said the first thing that you generate machine code, store it at location 12. None of these things generate machine code. The increment's the first thing that generates machine code, so that gets stored at location 12. And similarly, end doesn't generate any code. End is another assembler directive. It tells MPLAB this is the end of my program. If you don't say end, you get an error. And what's the error? It says it expected an end statement. So we're putting end in there. It doesn't actually generate something in in machine language. It doesn't actually create something in program memory that ends our program. It's purely just something that the assembler wants to see, to say this is the end of my program. Right? Why? Because how do you know that your file didn't just get truncated? If the last thing that you see is this, maybe there's some missing code there. If there is, I don't want to go ahead and run this. Or maybe that's the end of the program. So you put an end statement, you're telling the assembler, yes, and that's the end of the program. It's like the period at the end of the sentence, right? It tells somebody that's the conclusion. But it doesn't generate any assembly language, any machine language. All right, so these are assembler directives, right? And that's a good term to know. And it's something that directs or controls the assembler itself, MPLAB.
I have a question about the origin statement.
Okay.
So if you say you like did origin like 10, and then wrote a few lines of code, and then you did another like origin 10, and then maybe you wrote like a few less. So those would overwrite the previous ones, right?
Yep.
But then if you did less, there would still be some of the previous code in there. So would it increment to that code?
It's actually simpler than that. So if you try to build this, it'll complain. And somewhere in here, there's something that'll actually tell you this. So origin cannot fit the absolute section, and you have to work to figure out exactly what that means. But it's basically saying you wanted this instruction to go at location 10, and this would go at 12, and this would go at 14. And now you're trying to put this at location 10, and you've already put something there. And it'll just throw up its arms and give up right then and there.
Okay, so you can't overwrite.
You can't overwrite with this, no.
Okay.
Yeah, it's assuming that there's a problem in how you wrote your code. So if we're writing more complex code, typically you're going to want to make a memory map for yourself. And we'll do this more next week when we start talking about interrupts, but I will just do it next week. Basically, you want to start mapping out your program memory and say, this is going to go here, this is going to go there, this is going to go to this other place, and make yourself a picture of how you're going to organize your code in the memory, and then write your origin statements to reflect that. And you notice I can have an origin 100, right? That's location 256 in memory. I have plenty of memory in the program space. I should be able to go up to F00, right? These are valid locations in program memory. But if I try to put this at FFE, this would go at location 1000 hex. That's outside the available memory on this PIC processor. So again, I get this message cannot fit the absolute section. So that's hitting the boundaries of our program memory. All right, so that's one thing that you want to get some practice with is understanding where these instructions get stored in program memory. And I think I got some homeworks coming on that. A somewhat unrelated question, though, is as your program is executing, what's happening to the program counter? Okay? This is all about how I'm writing my program. I'm putting these instructions starting at 80, these instructions starting at FOE, and these instructions starting at 0. And so I end up with this stuff in memory at these locations. But if I start executing my code, what's the first instruction that's going to be executed? It's not this increment. It's at the top of my listing, but the processor doesn't care about my listing. When my processor starts to execute, it's going to execute the instruction at location 0, which is a branch instruction.
So the locations go in order, or is it just because of the branch is the reason why it'll execute it first?
It will always execute whatever's stored at location 0 in the program memory, which happens to be this instruction, this branch. But if I change that to, you know, just another increment instruction, right? When I run this code, it's going to increment location 80, it's going to increment location 80. What's it going to do after that? I have no idea. It's going to read whatever instruction is stored at location 4, and I haven't specified such a thing. So on physical hardware, it will read whatever happened to be there from the last time the chip was programmed, and it'll execute that. And maybe it'll execute something at location 6 and 8, and maybe eventually it'll get down to location 10 hex and start executing this code. Or maybe it'll go into a loop, or maybe it will crash. Don't know. And if I try to actually run this, so let's put a breakpoint down here. I think it'll be smart enough that it'll complain. So let's execute. So this is the first instruction that's going to be executed, and then it executes this next increment. And now okay, so it fell through, and it eventually got to program counter 10, and it executed this. But I think it's being smart, and it's filling in that other memory with no ops. If I did this on a regular processor, it's completely unpredictable what's going to happen. Just like after I do the add-con, well, no source code lines are found at the PC 1A4. Right, so it kind of freaks out. So let's talk about what the program counter does when you're running. When you power up the machine, it always starts at 0. That's defined in the architecture of the PIC processor. That's something called the reset vector. When you power up, or when you reset the processor, and you can reset it by pulling pin 5 down low. Okay, pin 5 is that MCLR line. If you pull that low, that does a reset. Program counter goes to 0. And then it just fetch decodes, executes, fetch decodes, executes, and so on. But there's a few exceptions to that rule, right? Normally program counter is incremented by 2 or 4, but there's things that will change the program counter value. One of them is a goto statement. Another is a branch or a conditional branch. Another is a call, which we're going to talk about next. Another is a return. And there's a few other things. But those are the main exceptions. So normally it's just going to execute sequentially. Alright, so let's run this. Alright, so we're going to put a 20 into W. We're going to move W into file register 80. So there's our hex 20 down there. Our program counter is 4. That's the increment instruction. We're going to execute that. We're going to put 7F into addcon 1. We're going to increment location 80. Our program counter is now 12. Normally, after we execute this instruction, our program counter would be either 14 or 16, depending on how long this instruction was. But because it's a goto, what this is actually going to do is change the program counter to the address of this increment instruction. So by executing this one goto instruction, the program counter changes to 4, and now we're back to the increment. Okay, that's how loops do their looping. Goto says change the value of the program counter to some particular value. And every time I get to that goto statement, the program counter is 12 and should increment to 14 or 16, but instead it changes back to 4. If you change the program counter, you've changed what the instruction is that's about to be executed. Okay, that's how we loop. And the coding of this, you can see, is coded as goto 0x4. Why is it 4? Because that's the address of the increment instruction. Now if I change my label to be down here, and I assemble this, my goto instruction now says goto 6. Why? Because 6 is the address of this move LW 7F instruction, which is what comes right after top. So these labels are basically saying, make this label equal to the address of whatever the next instruction is. So let's do something strange. Okay, so that's not exactly right. This label is the address of yeah, don't do this. If I wanted to do this, put the label after you've changed the origin, right? So this was instruction 4, so this label top is instruction 6. So when I say go to top, it's going to go to 6. So if you want to do something like this, put it after you've changed the origin. So now you assemble this. The goto statement says go to 80, which is the instruction after top. Alright, so gotos, branches, conditional branches are all kind of the same. We'll talk about coding them up later because the coding is a little strange. But let me talk about calls. So you know what functions are, right? From 121 and so on. Let's make a cool function. Alright, so here's a special function that adds 3 to file register 80. And just like in C, I'm going to put a return at the end. Alright, let's go ahead and build this. And let's execute this. So I'm sitting here at the top of a loop, and this doesn't do anything in particular. But I work my way down. My program counter is 6. I'm about to say call cool function, okay? here's what's going to happen. The address of cool function is going to get loaded into the program counter, and it's going to start executing all of this code. Okay, so remember, I'm right up here at line 7. I execute the call. I jump down here. I'm going to increment location 80. Increment it again, increment it again. I'm going to say return. What should return do? It should bring me back to line 8, right? So I execute the return. Now I'm here at line 8. Why 8? Because that's right after my call to cool function. And I do a few more useless statements, and I say call function cool func again at location 10. And so I jump down and execute this cool code. And now when I say return, where should I return to? This time I should return to line 11. And I do. And now I'm going to say call cool func once more, execute that code, and when I return, where should I return? Since I called it from line 12, I should return to line 13. And I do. And that says go to the top, and so I'll hop back up here and it starts over again. Okay, so what I want you to note about this is that when you say return from here, you don't always go back to the same location. One time I went back to here, another time I went back to here, a third time I went back to here. So how does this poor processor know where it's supposed to return to? Ideas?
There has to be some kind of code directing it after completing the increment, after incrementing it to the bottom, I guess 3 times. Since we have cool function 3 times, we should be able to say make an if statement, I think.
Okay, so something needs to be able to differentiate these different calls from each other, right? So that it knows when we say return, should we go here, or here, or here?
So does it keep track of the line number somehow?
Exactly, it keeps track of the line number somehow. So if we look at the code listing, right, this return, it's a really simple instruction, 0012. It's a 2-word instruction. There's nothing in there that says go back here or go back there or go back some other place. So there's a mechanism, and this is standard across almost all processors, conventional processors. There's something called a stack. And a stack, if you take CSE 224, we'll talk about stacks in depth, 222 in particular, but 224 a bit. Stacks are an example of a data structure. They're also called LIFOs, last in, first out. And here's the idea of a stack. You go to a salad bar, and there's, what is there? There's a stack of plates, right? And they're sitting in this contraption. It's spring-loaded. And there's one plate on top that you can take, and if you pull that plate off, all the plates below rise up a little, and there's a new plate on top. And somebody can take that plate off, and the next plate comes up to the top, and so on. And if you take a plate and you put it on top, everything gets pushed down, and the next person who takes a plate will take that plate that you just put on there. Okay? That's called a stack. And the last thing that was put on the stack will be the first thing taken off of the stack. And stacks, we don't really deal with anything other than whatever's on the top of the stack. So it's a special type of structure that you can basically add things to the top, take things off from the top. Okay, so our computer science terminology is push and pop. Push says add to the top of the stack, and pop says remove from the top of the stack. So the main reason we use stacks is because they let us implement this call and return strategy. So when a call is made to cool func, the processor does almost exactly the same thing as if we said go to cool func. But it does one extra thing. It takes the address of the next instruction, the program counter of that next instruction, and it pushes it onto a stack. So if we say call blah, processor does two things. Push the address of next instruction to the top of the stack, and then go to blah. And then when the processor gets a return instruction, it does two things. Remove from top of stack and save that value somewhere temporary, and go to whatever that address is that you removed from the top of the stack. So it reverses the process of doing a call. Alright, so call says take the address of the next instruction, push that on the top of the stack. And then go to, in this case, cool func. So it executes, executes, executes. We get to the return. It says take what's on the top of the stack, pop that off, and go to that address. Alright, so I'm looking at some other special function registers. Got my program counter. Let me get rid of some of these labels. We'll get rid of the decimal. Alright, so I've got the program counter. I've also got something called top of stack. Okay, top of stack is really 20 bits, so it takes 3 8-bit registers to see it, but I'm just looking at the low byte of the top of the stack. So TOSL shows me the value of the top of the stack, and stack pointer tells me how many things are on the stack. Okay, so let's just step through some code. So we're going to do a move 20 into W. We're going to do a couple of no ops. We're about to execute a call. Okay, our program counter is 6, and we're going to say call cool func. Okay, when I execute this call instruction, 3 things have happened. First of all, my program counter changed to 1C. That's the address of cool func. Secondly, the top of my stack changed to A. What is A? A is the address of the instruction following this call. Remember, this call was at location 6. Call takes 4 bytes, so the no op is at location A. And my stack pointer changed to 1, telling me there's one thing on the stack. What's the one thing? It's this A. Alright, so we're going to increment, increment, increment. We're about to do a return. When we return, what's going to happen? We're going to pop from the stack. So we're going to take this A and pull that off the stack. Stack pointer will go down to 0 because the stack will be empty again, and then we're going to go to location A. So when we say return, program counter changes to A, which means we jump back to here. Stack pointer is 0, saying the stack's empty. Now we come down here, we're at location E, and we're about to say a call. So this is E, so the address of this no op should be 12 hex. So when we say this call, 12 hex should get pushed to the top of the stack. Stack pointer will be 1, and we'll jump down to cool func again. So there's our 12 on the top of the stack. Stack pointer is 1, and our program counter again is 1C. and we're executing our cool func, and we're going to do the same return instruction we did a moment ago, but this time we're going to go back somewhere else. Why? Because we're jumping somewhere based on the stack. Return will look at the top of the stack, which is a 12. That's what it's going to jump to. So it's going to change the program counter to 12, which means now we're sitting down here. We execute instruction 12. We're about to execute instruction 14. The go-to is at location 18, so this call is going to push 18 onto the stack. Top of the stack is 18. Run our function. When we say return, it'll take that 18, set the program counter equal to it. That'll basically take us to our go-to statement. There's our return.
How many stack registers are there?
There's a single stack and it can hold 31 things. So the nice thing about stacks is we can make multiple calls that are nested inside each other. So cool func could call something else. And if we make a call to cool func, like this, don't really want to store. Let's go ahead and execute this. Alright, we're going to call cool func. So we've seen this before, right? It saves the address of the next instruction, which was A on the top of the stack. There's one thing on the stack pointer, and now we're executing cool func. So we do an increment, we're about to call this function called cooler. Okay, our program counter is 20 right now. The address of this next instruction is 24. When we call cooler, it's going to take that 24 and save that on the stack, which means the top of the stack will change to 24. But now stack pointer is 2. So when we push things on the stack, we can think of it like this pile of plates, right? The first thing we pushed, I don't remember what it was, I think it was 10, was on the top of the stack. Well, when we did the second call, we wanted to push a 24 on the top of the stack. And so this A basically gets moved down and 24 gets pushed on top. Make it 0A. So now our stack looks like this. And stack pointer is 2, saying there's 2 things on here. This is our most immediate return address. This was the prior return address. Right? And this is still saved. So after we return from our cooler function, this 24 will get popped off, this will go back to the top of the stack, and we'll be ready to return to our original location after our first call. So we're executing our cooler function, we say no op, we say return. We know we're going to return to what? Address 24. Right? So the program counter will change to 24, which brings us back here. Stack pointer changed to 1 and top of stack is now A. Right? What happened? This 24 got popped off, the 0A moved up, stack pointer changed to 1, and we're in exactly the same situation we were before that last call to cooler. So now if we say return again, we're going to go back to location A. So we come down here and do one more increment and do a return, and we pop off that A. That becomes our new program counter, and top of stack goes back to 0, stack pointer is 0. So what if we do this? What if we come down inside CoolFunk and we make a call to CoolFunk? Okay, we're in CoolFunk, our stack pointer is 1. The address saved at the top of the stack is A. That's the address following this first call. Well, we're about to make a call to CoolFunk, so the address of the next instruction, which should be 24, will get pushed on the top of the stack. And our stack pointer goes to 2. And if we make another call, we'll push another 24 on top of the stack. And the stack pointer will change to 3. So right now, this is what our stack looks like. We've made 3 calls to CoolFunk. The first return should come back to 24, the second return will go back to 24, and the third return will go back to A. But you know, I've got a problem here because I have an infinite loop set up, and I'm just going to keep calling myself while I'm filling up my stack. So I've got 31 things on my stack, and I told you the most our stack can hold is 31 things. So we're okay right now, but if I try to make one more call to CoolFunk, I'm going to have a problem. And it should have warned me about that, but it didn't. Oh, yeah, so look what happened. I came all the way back to program counter 0. So our processor just encountered an error, right? It's called a stack overflow. And we've tried to push too many things on the stack, and on the PIC processor, when you get a stack overflow, what does it do? It resets. It goes back to program counter 0. And I might have crashed my my MP Lab as a result. But on a PIC processor, it'll just reset back to 0. So that's an exceptional condition. And by the way, my top of stack is 0. My stack pointer is effectively 0, but that most significant bit of stack pointer, that's what tells me that I just got a stack overflow. All right, so we'll play more with stacks on Tuesday, and this will lead us into talking about interrupts on next Thursday. I will go ahead and I will post some homework questions later on today, and I'll put them up on Canvas. But it will mostly be, so I'll have you playing around with the access bit, right? Figuring out the access bit to access each of these locations, and then work through these questions determining the program counter of each instruction. And then some conditional questions, so I'll have you do these. I'm not going to have you do skip instructions. I'm not going to code branches. And we won't draw stacks. Okay, so this will be a short homework for this week. All right, I'll switch over to office hours. I will see you in there. Keep rocking on your labs, and I'll catch you there.